Myself, Karanam Ajit Assistant Professor, Vijayanagara College, Hosapete. Now in today's class we shall understand the thin film interference. Now before that we shall understand the division of amplitude. The amplitude of the incident wave is divided into two or more parts by reflection or refraction. The divided beams are made to reunite to give rise to interference bands. Now let us understand what is thin film interference. The production of colors when the thin films of transparent medium like soap film or oil, which when spread over water surface, which when being exposed to an extended source of light is due to interference of light. The waves which produces the multiple reflections and transmissions of light between the two surfaces of thin films. Now let me give you an example here. Whenever the oil which when spreads on the water surface, then which when being extended to the source of light, then we observe a colored pattern. This colored pattern is due to the phenomenon of interference. This is said to be the thin film interference. Now let us consider a thin film of thickness T and refractive index mu bounded by two plane surfaces xy and rs respectively. Consider the two surfaces xy and rs, which is of refractive index mu, which are being separated by a small thickness t. This t is the thickness of the film. When a ray of light which when being incident on the surface xy, that is AB is incident on the surface xy, then it is partly reflected along BC and is partly refracted along BD. So whenever the ray of light which when being incident, it is partly reflected along BC and is partly refracted along BD. Then at the point D, the same is the phenomenon takes place. A part of light is being reflected along DE and part of light is being refracted along DK. These two rays are such that DK is parallel to AB, which are in the same medium. The similar reflection and refraction takes place at the point E and G as well. Now let us consider for this reflected system. For this reflected system, if I draw EP perpendicular to BC, EP is perpendicular to BC, then the path difference between BC and EF is given by, that is BC and EF is given by, these are the two waves. The two waves that is given by BC and EF. The path difference between them is given by mu into BD plus DE. BD plus DE minus BP minus this component BP. Now let us find out this value is given by. Here BD and DE are equal. Therefore BD is equal to DE. That is equal to 2BD. Mu into 2BD minus BP. Let us call this as the first expression. Now let us find this value of BD and BP to identify this component of path difference. Now to find BD, let us consider the triangle BDQ. The triangle is BDQ. In this triangle, we have to find out the cos theta. Cos theta is given by, here this is the right angle. The opposite to right angle is hypotenuse. DQ is adjacent side. BQ is opposite side. This is opposite to this particular angle. That is given by opposite side. So cos theta is cos R. That is equal to DQ by BD. Adjacent by hypotenuse. dq by bd, or bd is equal to dq by cos r. dq is nothing but t, that is equal to t divided by cos r, that is given by the first expression. Now let us find out the value of tan r, the tan theta. Tan theta is given by opposite by adjacent side. Opposite is bq, adjacent is dq. Therefore, it is given by bq by t, or bq is equal to t into tan r. Now, let us find out these values here. To find this value of bp, let us consider the triangle BEP. BEP is a triangle. In this triangle, we have to find out this component here. So, in the triangle BEP, the sin I is equal to BP by BE. That is equal to BP by BE is nothing but BQ plus QE. So, from this triangle, sin I is equal to BP by BE. BP divided by BE can be written as BQ plus QE. So, BQ is equal to QE. They are equal. Therefore, it is equal to 2BQ. That is given by 2BQ into sin I is equal to BP. So BP is equal to 2BQ into sin I. BQ is given by T into tan R. T into tan R into sin I. That is equal to 2T tan R into mu sin R. Or it can be written as 2 mu T tan R into sin R. That is equal to BP. Therefore, BP is equal to 2 mu T into tan R into sin R. Tan R is given by sin by cos into sin R. That is equal to 2 mu T into sin R into sin R is sin square R divided by cos R. Now, substituting these two values in the equation 1, then we get the path difference 2 mu into BD minus BP. Now, let us substitute this component of BD and BP here. That is equal to 2 mu into BD is T by cos R minus BP is given by this component 2 mu T sin square R by cos R. Here we can take 2 mu T common. We get the first term is 1 by cos R minus sin square by cos R. The common denominator. For common denominator, numerators can be added or subtracted. That is given by 1 minus sin square R by cos R. Therefore, 2 mu T into 1 minus sin square R by cos R. That is equal to 2 mu T into 1 minus sin square theta is cos square theta. That is given by cos square R by cos R. One value of cos R cancels. That is equal to 2 mu T into cos R. Therefore, since the rays is reflected from an optically denser medium at the point B suffers phase difference of pi, which is equivalent to the path difference lambda by 2. Therefore, the actual path difference between the two waves is given by, that is for reflected system, is given by 2 mu T cos R minus lambda by 2. This is depending upon the path difference of two reflected rays, the film appears either bright or dark. Now let us understand the condition for bright and dark fronts. Now for bright band to produce, the path difference is n lambda. That is given by 2 mu T cos R minus lambda by 2 is equal to n lambda. Now if you transfer lambda by 2 here, it becomes plus lambda by 2. N lambda plus lambda by 2, that is equal to 2n plus 1 lambda by 2. Therefore, for bright band to produce, the path difference is 2 mu T cos R is equal to 2n plus 1 lambda by 2. Whereas for dark band, the path difference is 2n plus 1 lambda by 2. That is given by 2 mu T cos R minus lambda by 2 is equal to 2n plus 1 lambda by 2. Or 2 mu T cos R is equal to, if you transfer it becomes plus lambda by 2. 2n plus lambda by 2 plus lambda by 2. Here if you take lambda by 2 common, it becomes 2n plus 1 plus 1. That becomes 2n plus 2. If you take 2 outside, this 2 cancels. It becomes 2n plus 1 lambda by 2. That is equal to n plus 1 into lambda. Therefore, the path difference is given by 2 mu t cos r is equal to n plus 1 lambda. For dark band, the path difference is 2 mu t cos r is equal to n plus 1 lambda. Now let us consider for transmitted system. The path difference between the two transmitted rays dk and gh is similar and is equal to 2 mu t cos r. The path difference is 2 mu t cos r. In this case, there is no phase change on the reflection at the point E, and as it takes place at the surface of the rarer medium. So this is the reflected surface, or this is the reflected the waves, and these are transmitted waves. So this now we are considering for this transmitted system. For transmitted system, these rays dk and gh, these rays, the path difference between dk and gh is similar and is equal to 2 mu t cos r. Therefore, the path difference is 2 mu t cos r. So when the thickness of the film is very small as compared to the wavelength, so that 2 mu t cos r is negligible. The two rays will be in phase and thereby these will reinforce with each other. Then whenever the two waves reinforce with each other, then it produces a bright band or a bright fringe that is being produced. As the thickness of the film increases, the film appears bright. The path difference is given by 2 mu t cos r is equal to n lambda. This is for the condition of bright fringe. For bright fringe, the path difference is 2 mu t cos r is equal to n lambda for transmitted system. The film appears dark if the path difference is given by 2 mu t cos r is equal to 2n plus 1 lambda by 2. This is the condition for dark band to produce for the transmitted system. Now it is very clear from the path difference that if a bright fringe is produced in the reflected system, a dark fringe is produced in the transmitted system for the same path difference. For transmitted system, the film appears dark and is given by 2 mu t cos r is equal to 2n plus 1 lambda by 2. For the same condition for the reflected system, 2 mu t cos r is equal to 2n plus 1 lambda by 2 produces a bright fringe. Therefore, if the bright fringe is produced in the reflected system, a dark fringe is produced in the transmitted system for the same path difference. Thereby, this shows that the reflected and transmitted systems are complementary. The reflected and transmitted systems are complementary. That means when it produces a bright fringe in the reflected system, for the same condition it produces dark fringe. That shows that reflected and transmitted systems are complementary. This is very important condition. Thank you.